thing.
I'll give it to you tomorrow at lunch.
Okay, appreciate that. Okay. Critically acclaimed film Interstellar by Christopher Nolan is regarded as one of the most scientifically accurate movies of all time, winning the 2015 Academy Award of Best Sound Design as well as a multitude of other nominations. The film displayed the first rendering of a black hole and applications of general relativity's time dilation, with mentions to the theory of everything, what was known as the standard theory, the hypothetical idea of a united framework of physics. The scientific advisor for this film was acclaimed astrophysicist Kip Thorne, who, along with a team of physicists, calculated and simulated the time dilation gravitational effects in the black hole Gargantua. The lecture series hopes to examine the accuracies and inaccuracies pictured in Interstellar, as liberties were taken from the simulated and advised properties of the interstellar cosmos. This analysis is organized as follows. Section 2 is like broken into different sections. Section 2, which is like basically chapter 1, I guess, presents the black hole Gargantua and covers the gravitational effects it would have on surrounding planets. Section 2 will also cover velocity needed for the gravitational assist maneuver taken by Joseph Cooper, who's a character in the movie, and his crew, as well as the forces on the ship. Section 3 will detail the theory behind wormholes, around centers and bridges, and it will also cover the feasibility of interstellar travel in relation to wormholes, and look at Interstellar's adherence to scientific accuracy in this area. So, obviously, I just gave a bunch of words to you that you probably don't understand at all. To understand this, I figured an overall explanation of the physics of a black hole is required because, I could just get into it. Sorry, I have a question.
Can you slow down?
That was me just getting through the preamble, and now I'm going to slow down.
Okay. Can you talk louder?
Sure. Okay. To understand this, an overall explanation of physics of a black hole is required. Black holes are the quintessential example of an object made from space-time. Actually, I guess I can go back to this because we're not there yet. But, so first of all, what's a black hole? I should also say today's lecture will help to provide a foundational understanding of black holes and explain concept of general relativity, which you don't really get into in high school, so I figured it's important. So first of all, what's a black hole? They are celestial objects which have such a large density or a gravitational pull that even light cannot escape it. So you might think of, you might wonder, how is this thing created? Most of the time, it's when a star collapses because it's been around too long, and stars kind of work where they have a ton of energy, and energy gets shot off, but then when they get shot off, they shrink in size. So the sun's shrinking right now, or it's actually growing right now because it's in the first stage of it. But after they expel most of their energy, they get to a point where they start to shrink, and upon shrinking, they get tighter and tighter until they basically get so dense that they explode or they turn into a black hole. And like a supernova, that's an example. So their diameters are much larger than their circumferences, which is possible because the plane of space-time could be pictured in 3 dimensions. You have 2 dimensions, with a 3rd dimension and the diameter extending down through the traditional field of space-time to reach the singularity. So singularity is down here. You have 2 dimensions of space-time, and then it's a 3-dimensional. Or if it was if space-time was 2-dimensional, a black hole would be 3-dimensional. So it would have a pull down. It's going to get a lot into the different dimensions and how that looks on different coordinates and such. In other words, it takes far longer to traverse through a black hole than to go around it. So I don't know if you've ever seen a black hole. I haven't personally. But you would probably not want to actually go through it because that would hurt. And it would also take a while. And kind of impossible, low-key, but it's okay. If you want to go through it, the diameter would be much larger than the circumference, which is not normally the case if you were in geometry. Yes, question.
Okay. How do we know that it would hurt?
I actually get into that, not this presentation, but a different presentation. There's something called spaghettification.
Spaghettification?
Yes, you become spaghetti.
Oh.
Like how Mr. Fantastic becomes spaghetti in, what's the movie, Multiverse of Madness?
So a spaghetti maker is basically a black hole.
No.
I think that's what it's
would be fine.
It's actually a really interesting thing in physics. Spaghettification is not a simple concept. It's actually very complex. Yes, question. I'm going to move on if you don't ask a question.
I was joking.
How do we know it's impossible?
I get
Okay, sorry.
everything you... Okay.
Excuse my choking.
Yes, sorry.
What's your favorite Marvel movie?
Can I please stay on topic?
Yeah, please.
That is topic.
No, it's not actually.
It's trivia.
Okay.
I'm not
In other words, it takes far longer to traverse through a black hole than to go around it. All objects warp space-time in a way that produces a gravitational effect, like this thing. This produces a gravitational effect. Surprise. Um, but it is only noticeable at a very large scale because of the very small scale of the universal gravitational constant, which is, if you take a physics class, you'll know it's 6.67 EE, which is, and it's in very weird units. But basically, it's a very, very small force. Like, you'd have to be at a very, very large scale for it to feel an effect. We can measure the orbits of celestial objects like our Earth and Moon without worrying about like why a gravitational effect is caused, because time and light are not affected much by objects at the scale of just the Earth or Moon, which may seem gargantuan because we're humans, but in the grand scheme of things, they're actually not that dense or big. So black holes are celestial objects for which this is not the case. Their mass to density ratio is so great that space-time around them warps, and time dilation is obvious to a human observer, which creates another effect called the Schwarzschild radius, or the event horizon, which I will explain. So you may have heard of event horizons. You can see Schwarzschild radius, or event horizon. You may have heard of them as the point of no return. When something is pulled through the event horizon, it can't escape from the black hole. To understand the fundamental path of objects through space-time and why time slows down for a distant observer as someone nears the event horizon of a black hole, which I'm going to get into, we need a way to represent space-time as a single two-dimensional plane upon which space-time events occur, like black holes. For our purposes, consider the question, where's the writing thing, Mr. Cordero?
I think you have to put it in, or is there a draw thing?
No, like, well, I wasn't going to draw on this. I was going to draw on the blank thing.
Oh, sorry. And it's on the black border, right above the three dots.
Aha, thank you. Fancy technology. Okay, what was I doing? Okay. Actually, I'm not going to write this out. How do I? I'm going to delete that. Okay, never mind. Let's just go back to the main thing for now. So the question is, how could I represent a three-dimensional object using two-dimensional means? Example. This question is most practically found with relatively simple shapes, like pyramids or cubes or other prisms, which can be split into squares or triangles and the like. This is actually where it'd be useful to have this. Like if you have, like this, you can see how this can be split into, split into triangles and it can be split into squares. So what if you're dealing with objects that don't have simple planes, like a sphere? A sphere doesn't have simple things like that. It's similar to the principle of calculus, if you take calculus, and find the length of a curve by taking a composition of lines with an infinitely decreasing length. So that's a way of approximating, if you haven't taken calculus, that's a way of approximating, like if you're trying to find the length of a curve, you can find the length of a bunch of small curves, like just get like lines. You know how to find the length of a line, it's just rise over run. So just do that over and over and over again with, there's a mathematical operation you can do to make that go to where the sides are so infinitesimally small they're undetectable, and you just get the actual thing, basically, because infinity works like that. For shapes like domes, you can do the same thing. You can take an area and shape of the dome by composing the areas of planes with an infinitely decreasing size. For black holes, we can do this using the plane of space-time. Objects always follow straight lines over space-time, which is a very, very important principle. If you're taking notes, write that down. To demonstrate this and to better conceptualize it, let's examine a stationary observer compared to an accelerating observer. So imagine someone is in free fall. On Earth, this could be if somebody is jumping off the Niagara Falls, and Niagara Falls has also been somehow contained in a perfect vacuum that doesn't have air resistance. For someone who's on the observation deck in Buffalo, they would see you accelerating as you plummet to your demise. But as a person who's falling, you notice something different than if you're not falling. Well, I guess you could observe it if you weren't falling, but it'd be kind of like unintuitive, I guess. If you were falling in free fall, you could drop objects from your pocket, and you just see them stationary to you as you fall, which tells us that if you fall, you can remove gravity because everything's relational to itself. Sorry, what was your question?
You said objects always move in a straight line. Is that what you meant?
Yes, through space-time.
Through space. Wow.
So wait. I'm not chatting with Copilot. Not now. Okay. To quote science communicator and writer Brian Cox, whose book I'm reading, very good book, if you should check it out if you haven't. It's called Black Holes. Gravity appears now because there is a fundamental force of attraction between things, as we learn at physics classes in school, but because, sorry, it says now, but it should be not because there is a fundamental force of attraction between things, as we learned at physics classes in school, but because small patches of space-time are tilted relative to their neighbors in the vicinity of massive objects, which is a lot of, it's supposed to be a breakdown, but I'll break it down further, which is, in other words, it's easier for objects to move in a straight line than to deviate from this course, so they move in straight lines through space-time. And space-time is you can represent space-time as a composite of smaller, like squares, as we were showing of space-time. So this is also a very fundamental principle. It's kind of related to what I said. If it takes more action which is basically just a physics word for stuff, it's literally basically what it means. If it takes more action for an object to actually do something than to not do something, it will not do that thing, which is, I would say, probably the fundamental driver for all of physics. In Newtonian physics, this is Newton's first rule, which says objects in motion tend to stay in motion, while objects at rest tend to stay at rest. Very famous. It's the same thing for an object moving through space-time. An astronaut that does not accelerate takes a path over space-time between two events that maximizes the time they measure on the wristwatch between those events, which I can explain further if you don't really understand that. But you want me to explain more?
Yes.
Okay. Let's see. Bro, come on. Okay. So, say I'm walking to school. This is going to be bad because I don't have a graph set up. But imagine I'm walking to school. I'm going like that. It's beautiful, beautiful morning. What if every 20 seconds let's say I live really, really far away from my school. Let's say it's like your parents used to say, and you're like, it's like I'm walking to Olympia for school. Every hour I take while walking, my wristwatch does a beep. So let's just say, if this is me here and this is Olympia, every hour, I'm assuming this is going to take a while. It's probably going to take longer than that. I put a wristwatch goes off, or a wristwatch beep goes off and it records basically what time I do that. Now, what if I was, instead of walking to Olympia, I was walking adjacent to a black hole? That's kind of a hard example. But let's say, no, actually, what if instead of walking, I was driving to Olympia? And as I was driving, I was driving with a bit of panache, a bit of, let's say I was going crazy on it, you know what I mean? So let's say I was just like accelerating, deaccelerating over and over again. Now for the first mile, I'm just cruising along, you know, I'm at my snail's pace, 5 miles per hour. Actually, I'd probably be faster than if I walk. And it's like, okay. And then let's say I stop and eat a burger at I don't know any burger places between here and does Dick's have a burger place? I guess they have to have a burger place between here and Olympia. No, between here and Olympia. I mean. I'm just gonna say I stop here, and I stop there. Bang. Hang out there for a bit, and then I continue. Let's see, 1, 2, 3, 4, 5, 6. I continue. I go really, really fast because I feel, wait, I have to make it there in time. And then I realize I actually don't have to because I went too fast. And then I go to a rest stop because I don't know, I don't know why I'm at a rest stop at my destination, but I'm at a rest stop. And then I continue further, and then I just drive at a steady pace. So even though it's the same amount of ticks per se, or maybe this is a bad example, but like, imagine I didn't do this actually. Imagine I was just doing like that. The An astronaut does not accelerate, takes a path over space-time between two events that maximizes the time they measure on the wristwatch between those events. So if, let's say I didn't do that, I just ignored this line, and it actually only took me 5 to get there. Then if I hadn't been accelerating, I wouldn't have been like that. Because this maximizes the time it takes for me to, because this is me walking at a steady pace. This is me when I'm accelerating and such. Here, I'm just at a pace, and I'm maximizing the time that I am going between these two events, basically. Because this is the max I can walk at a steady rate. It's like a perfect rate. And then here, I'm not doing that. So, but to do that, I have to accelerate. I have to deaccelerate too, but it means I have to deviate from my natural course, which would be to walk in a straight line. And so that's kind of what happens as you're in space-time, which is you deviate from your expected line of something by accelerating. So an astronaut who does not accelerate takes a path over space-time between two events that maximizes the time they measure on the wristwatch between those events, because time is it's not a fundamental aspect, I should say, but the maximum time is a fundamental aspect, because that requires you to, because there is a universal limit on how fast you can go, which is the speed of light. Because no object can go past that speed of light. There is always a path. Like, even if I'm walking, this is not naturally, I would not naturally, if I wasn't walking at a steady pace, I would not naturally just go to Olympia. There is a rate at which I would go there, and it's never, basically, because, I mean, these two events are close, but, sorry, no dissing on Olympia, but, I have nothing against Olympia. But as you, acceleration changes your maximum time, or changes, not your maximum time, it changes the time you take to get between places from, I would say, the natural course of what you would go. So does that make more sense? Okay. I just had a heart attack. So that's why the moon stays around its orbit in Earth, and the Earth around the sun. I think it goes back here. And to not continue this orbit and to randomly fly off into distance would be to follow a non-straight path over space-time. And to do that, there'd have to be something to accelerate them, because these objects do not have will like I do and cannot take a car. They are stuck here, basically. And everything they do is influenced by each other and not any kind of cosmic, actually I guess this is cosmic, but not any kind of self-individual action. So celestial objects made an impression on space-time, as you can see on the right. And this causes the space-time curvature to warp. Oh wait, are we at end of class?
Yeah.
That was the bell. Okay.
That was really good.
Yeah.
Just such a big
Hold on, stop.
Stop.